Assalamualaikum warahmatullahi wabarakatuh. My name is Amira Aisyah binti Kamar Zaman and my matrix number is 084108. We will be presenting our project, which is System Distributed Restaurant Booking, that demonstrate core concept in distributed systems like multi-threading, naming service, replication and consistency models using Java. Our system simulates a restaurant booking platform with multiple branches. Each client makes booking requests that are handled by different nodes with help from a naming service to locate them. The architecture includes multi-threaded clients, replica node for data storage, and a consistency manager to keep the data synchronized. The main component include main.java to start the simulation, naming service.java for branch name resolution, booking thread.java for client booking request, replica.java to store booking data, and consistency manager.java to manage how data update across replica.
Naming system design, comparison between flat and structural naming. Point 1 is flat naming. Offers a direct mapping between names and entities which are usually kept in a structure resembling a dictionary like. Point 2 is structural naming. Incorporates hierarchy like DNS tree and might support wildcard queries or delegation. Point 3 is the reasons for choosing flat naming. Java's HMAP is used to implement flat naming. It is perfect for simulation because first is easy use and straightforward search. Second is avoiding the hassle of managing a distributed or hierarchical naming system. And third is a level of realism appropriate for educational purpose such as branch.restaurant.com to the node A.
The system shows replication to improve reliability and availability. Two consistency models are supported, which is eventual consistency where replicas sync over time and sequential consistency where updates happen in strict order. This helps illustrate the trades-off in the CIP theorem.
First is architecture diagram. This diagram illustrates the key components and interactions within our simulated distributed booking system. So the component breakdown is clients. Clients represents customers making booking requests. Each request is processed in its own thread, simulating concurrency. Second is naming service. Naming service acts like a DNS system, maps human readable branch names like branch1.restaurant.com to internal node identifiers like node A. Third is booking threads. Each booking request is represented as a booking thread. It interacts with the naming service that initiates a booking through the consistency manager. Next is consistency manager. It controls how booking data is synchronized across replicas. It supports two modes. First is sequential consistency and second is eventual consistency. Lastly is replica nodes, replica A and replica B. It simulates distributed storage and store booking data redundantly for fault tolerance and availability. So here's how the interactions happen step by step. First is client initiates a booking request. Second, the request is passed to the naming service to resolve the branch. Third, a booking thread is created and started to handle the booking. And fourth, the thread passes the booking request to the consistency manager. Fifth, the consistency managers update replica A and replica B. If sequential consistency is selected, both replicas are updated immediately and in order. If eventual consistency is selected, replica A is updated first and replica B follows after a delay. And lastly, the update results are displayed on the Java console output, showing how each replica received the update. Next is process flow diagram. This diagram illustrates the full life cycle of a booking request in our simulated distributed systems. Process flow breakdown is first start or client request. The process begins when a client initiates a booking request, like reserving a table at branch1.restaurant.com. This is simulated using a Java thread to represent concurrency. Second is naming service resolution. The system uses the naming service to resolve the branch name to an internal node or object reference. Think of this like a DNS branch1.restaurant.com to the node A. Third is thread creation. Once the branch is identified, a booking thread is created. Each thread handles a separate client request, simulating parallel client activity. Fourth is consistency manager invocation. The thread invokes the consistency manager to process the booking. The consistency mode selected sequential or eventual determines the update behavior. Fifth is replica update. The consistency manager updates replica A first. Then based on the consistency model, sequential consistency, replica B is updated immediately. Then eventual consistency, replica B is updated after a delay. Set is booking confirmation. Once replicas are updated, the booking is confirmed. A confirmation message is displayed in the console. And lastly, end or output. The output shows how and when each replica received the update. And output also helps verify whether the consistency model worked as expected.
The whole system is built in Java using NetBeans. We use Java threads for concurrency, hash maps for naming, and synchronized blocks to manage consistency. All outputs are printed in the Java console.
Hi, my name is Nurul Aim Izzati binti Muhammad Noor and my metric number is 083348. I will be presenting the simulation part of our project. The simulation models a distributed restaurant booking system using Java. It shows how the system handles booking requests by simulating concurrency, name resolution, and data consistency using replica. We implemented two consistent models, which is even, dual, and sequential. Next, we go to the simulation components. Our system consists of 5 main Java classes. First, main.java that runs the simulation. 2. Naming service.java that maps each branch name to a server node. Each booking is processed in a separate thread using bookingthread.java. The booking is saved into 2 data nodes or replica using replica.java, and consistency manager.java controls how and when the replica are updated. The key features implemented. The simulation use a flat naming approach implemented with hashmap, which allows easy resolution of branch names to nodes. It also used Java threads to simulate multiple customers booking at the same time. Each booking is replicated of 2 nodes, and we switch between 2 consistency models, which is even, dual, and sequential. Even, dual consistency output. Here we run the simulation using even, dual consistency. As you can see that replica A, which is tempahan untuk Ali, is updated first, followed by replica B, which is tempahan untuk Siti after a delay. This simulates a real-world scenario where data eventually becomes consistent across all nodes, but not immediately. Sequential consistency output. This time, we use sequential consistency. Both replica A, which is tempahan untuk Ali, and B, which is tempahan untuk Siti, are updated immediately and in the same order, which is there is no delay. This ensures the system remains consistent across all replicas during booking operation. To conclude, our simulation clearly shows the difference between even, dual, and sequential consistency. Even, dual consistency allows for delays but improves flexibility and performance, while sequential consistency ensures strict ordering and synchronization. This project helps us visual how the distributed system works in practice.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nurdina Iwani binti Yusri. My number metric is 083349. Today I will present an analysis of a naming module trait of flat bed versus naming structure. In a distributed restaurant booking system, the naming model plays an important role in how the system identifies and manages key elements such as restaurants, branch, table, and realization. A good naming model ensures smooth communication between distributed components and simplifies the process of searching, storing, and retrieving information. Flat naming uses simple, unique identifiers that do not carry any extra meaning. For example, a reservation ID like RES 20384 does not tell us which restaurant or table it belongs to. Structure naming use hierarchical or descriptive names such as /bin/ban1 /table12, which instantly shows location and table details just by looking at the name. Process versus trait-based design, which is in a distributed restaurant booking system, the system must respond to many user requests at the same time, such as checking table availability, making reservation, or cancelling booking. To handle this high concurrency, a decision must be made between using a process-based or trait-based architecture. 1. Process-based design, which is task or user requests run in a separate process. Processes are isolated and have separate memory space. Safer, a crash in one process doesn't affect other, but more memory is saved. Slower communication between process, example via inter-process communication. Trait-based design, trait share memory within a single process, lightweight and faster to create than processor. Can handle many simultaneous user with lower memory overhead. Threads can communicate easily but need to be carefully synchronized to avoid bugs, like two threads booking the same table. Consistency model evaluation in restaurant booking consistency ensure the same table is not booked twice. The choice between consistency model affects speed, reliability, and conflict handling. Eventual consistency used for displaying table availability. Pros: fast, highly available. Cons: might show outdated info. Sequential consistency used for confirming table booking. Pros: accurate, avoid double booking. Cons: slower due to synchronization.
Scenario Analysis 1. Scenario 1 is about node delay. In this simulation, node A has had a 3-second delay in syncing data. With eventual consistency, other nodes continue processing bookings, maintaining speed but risking conflict. In contrast, sequential consistency delayed responses to ensure all nodes agreed before proceeding. This shows how eventual consistency prioritizes availability while sequential consistency focuses on accuracy. Scenario 2 is about concurrent bookings. Two users tried to book the same table at the same time from different locations. With eventual consistency, both bookings were accepted locally before syncing, causing a conflict resolved by keeping the first and rejecting the second. Sequential consistency prevented this by allowing only one booking, maintaining a strict order. This highlights how different consistency models handle race conditions in distributed system. This is comparison of consistency models tables. Eventual consistency, faster response times, high scalability may lead to temporary data conflicts, better fault tolerance. Sequential consistency ensures data accuracy across all nodes, slower performance due to synchronization, less scalable and flexible, stronger data consistency guarantees. Conclusion highlights trade-off between performance and consistency in a distributed restaurant booking system. Conclusion: eventual consistency, more practical and scalable for restaurant booking systems. Risk of booking conflicts, but manageable with timestamp first confirm booking priority. Sequential consistency, since delays reduce user experience, less resilient to node failures. Eventual consistency offers better performance and fault tolerance, making it more suitable for real-time booking needs. The recommendation: use eventual consistency. It is faster and more scalable, making it ideal for real-time restaurant bookings. Users can make reservations quickly without waiting for system-wide updates. Add conflict resolution. Since data might be temporarily inconsistent, use simple rules like first request wins to handle booking conflicts automatically and fairly. Implement local caching and fast syncing. Local caches speed up access, and quick syncing between replicas reduces inconsistencies. This improves performance and keeps data fresh, especially during busy times.